Hello, scholars. It's late on Sunday night after Thanksgiving weekend. I hope you all had a great break. I did, but now we've got to get down to business of our last unit. So I'm going to try to cover 2 lessons in one video here. A lot of it's review from Algebra 1 and Algebra 2. So I'm going to start with that. Remember in Algebra 1, we learned how to solve a system of equations. And what that meant is we'd have a linear equation and we'd have another linear equation. And we were trying to find the point where those 2 linear equations graphically intersected. Algebraically, we were looking for the one point, the xy value that would work in both equations. And we focused on linear systems. It's also possible to have a quadratic and a linear system of equations and look for their intersections, which could be more than just one point. And then, of course, remember we had the possibility of 2 systems, or a system where the equations didn't cross at all, so we could get no solution. And so now imagine that we have all different kinds of shapes. We could have a polynomial, and we could look to see if a linear equation crossed that polynomial. We could have an exponential equation, and we could see if a quadratic crossed that exponential equation. So there's all different types of systems of equations. And then inequalities is where you have these types of situations, but you have less than or greater than. So you have a shading situation, right, where maybe you have one line that's shaded like that, and then another line that's shaded this way, and so you're looking for the intersection of those 2 shaded regions, and instead of finding 1 or 2 solutions, you have a whole region of solutions. So I'm going to briefly review what a system of linear equations looks like, just so you remember it, and then we'll go on to more pre-calculus type problems. So my first example is just a simple linear equation where the 2 equations are written in standard form, and you're trying to find whether or not they have an intersection point. And so we had 3 methods for doing this. Our first method was to graph the 2 and literally look for the place where the 2 lines crossed. But we very quickly found that that was not very practical because they didn't always cross at a nice even point. We needed graph paper. It wasn't very accurate when we drew our graphs, so we didn't use graphing really except to visualize the fact that we were looking for the intersection of those 2 lines, like on the picture that I have over here. So we had another method called the substitution method, which worked really well if you could solve one of the equations for a single variable, and you could rearrange it and then substitute it into the other one. And that strategy of substitution works for a lot of things, so you probably remember it. This system would work well for that because you do have y by itself right there with a coefficient of 1. So you could rearrange the equation, solve for y, substitute it in, and you could find the solution. The third method was the one that you guys liked the best, and that was called the elimination method. And the idea of the elimination method is that you can adjust one or both of the equations so that you can combine them and make one of the variables disappear. So that's probably the method you guys would have chosen if I gave you, your choice of how to do it. And I'm guessing that probably most of you would have gone like this. You would have taken that first equation and you would have multiplied it by positive 3. That would have made it 9x plus 3y equals 7. Keeping the second equation exactly as it is, now we can add these 2 equations together and we see that did I do something wrong there? Oops, yeah, I forgot to multiply this times 3 also, so that should be 21. I knew that didn't look right. And so that gives us, 33 when we add those 2 together. But notice how the y variables canceled out. We get x equals 3. We plug 3 back into the original equation. And just to save time, I'll tell you that it equals negative 2. So that is the point of intersection. If you look over here at the picture, that would be the dot, the point where those 2 lines cross, the only xy value that works in both of the original equations there. So it's also possible to have no solution. When you get a no solution problem like this, it means there is no intersection, and you'll get a non-true statement like 0 equals 5. Basically, both of the variables will cancel out on one side, so you'll have 0, and then you'll have another number over on the other side, and you'll know that there's no solution. Sometimes you get an infinite number of solutions. Remember when one line is right on top of the other line? So we have no solution, we have one solution, and then we have an infinite number of solutions, and when that happens, you get something like 0 equals 0. And that's how you know that it's an infinite number of solutions. So seriously, we learned that back in Algebra 1. We re-emphasized and learned that in Algebra 2. So I'm not going to do examples of that for you guys. We did a lot of those, and I know that you guys could do those. But we didn't do that many word problems like that. And so I'd like to go over a few word problems with you. I should have typed up the word problems. I just realized that. I'm going to keep going anyway, since I already started here. Okay, so the first word problem that we have, it says that a certain heritage performance costs $3 per student. That's the student ticket price. And it costs $5 per adult. And we know that 400 people attended. And we also know that they brought in $1,480 in ticket sales. And so the question is, how many adults and how many students attended? We did some problems like this. We did the quarter, nickel, dime type problems. So basically you take the information, you turn it into two equations, and then you solve the system. So you have to pick variables. You can pick X and Y, or you can use something else if you want. Let's say X is the number of student ticket, and Y is the number of adults. And basically we just say, okay, X plus Y equals 400. We know that 400 people attended. Maybe it was 200, 200. Maybe it was some other split. And we also know that $3 per student ticket plus $5 per adult ticket gave us a total of $1,480 in sales. And then you solve the system just like we did above, and you can figure out how many adults and how many students there were. Again, we did a lot of problems like that. Setting them up was the hard part, but you guys got pretty good at that. Okay, the next one we did not do. This was a distance equals rate times time problem. I always thought these were kind of hard, but if you follow the format that I'm going to teach you, it'll be easy. We're going to use this basic formula from physics that distance equals rate times time. So for example, if you're driving 60 miles per hour for 5 hours, that's your rate, that's your time. Multiply those together, you get your distance, 300 miles. So we can use that formula for problems like this. Jill leaves Seattle at 8 a.m. and averages 50 miles per hour. Bob leaves San Diego at 9 a.m. and averages 65 miles per hour. So let me write that down. Jill, she leaves at 8 a.m. She goes 50 miles per hour. You've got Bob. He leaves San Diego at 9 a.m. and drives 65 miles per hour. When do they meet and how far are they from home? Note that the distance between them, between their two cities, Seattle and San Diego, is a big 1,255 miles. Wow. These guys really want to meet in the middle. Okay, so what we're going to do is we're going to set up two different distance formulas. We're going to say the distance that Jill travels, I'll call it D with a little subscript of J, is going to be 50 miles times however long she drives. And the distance that Bob travels is going to be 65 miles, but he's not going to drive as long because he left later. He left an hour later, so his time is going to be one less. Wherever they meet, he's going to have driven one less. Altogether, their distance is 1,255 miles, and it has to equal 50t plus 65 times t minus 1. So, basically, if you solve that, I'm not going to go through the algebra with you because you guys are all awesome at doing algebra like that. Distribute. You're going to get t equals 11.478 hours. So, if you start from when Jill left at 8 a.m. and you add 11 hours, that puts it at 7 and something. You can figure out what portion of an hour it is. 0.478 is actually 28 minutes. So they meet at 7:28 p.m. And you can figure out how far each one of them drove if you multiply their rate. 50 miles per hour for Jill, times 11.478. And then the same thing for Bob. He went 65, but he went one less hour, so 10.478. And you can figure out how far each one of them drove. All right, so distance equals rate times time problems. You might need that formula. All right, and then the last example is a mixture problem. Mixture problems also, sometimes very confusing, but if you follow the format that I'm going to teach you, you'll know how to do it. Okay, so this is going to say we've got 20 liters of a solution that's 50% acid, okay? And it's obtained by mixing a 40% plus some 65% solution. So you mix these two and you get an acid that is in between those two as far as concentration, the percentage of the acid. So the question is, how many of each liter was used to get that combination? So first thing we're going to say is let's let X equal the 40% solution, however much of that we add, and let's let Y equal the 65% solution. And we know that so many liters of X plus so many liters of Y equals 20. Okay, and then we also know that the 40% solution is only 40% acid. The 65% solution is only 65% acid. So as far as the amount of acid that's actually in that 20 liters, it's 40% from something and 65% from something. And then that's our X and our Y. And it gave us 20 liters at 50% solution. So now we have two equations with two unknowns, and you can solve it using either substitution or elimination, either way. And I'm just going to, again, skip the algebra on this because I know you guys are good at that. And you're going to end up getting that Y equals 8 and X equals 12. And you can check and it works out just fine. Okay, so that's my brief review with you guys of linear systems of equations from back in Algebra 1 and then Algebra 2 with some more advanced word problems thrown in there. Okay, now what about inequalities? An inequality is different from an equation because it has a less than or greater than, less than or equal to, greater than or equal to sign. Its solution is not just a single number or a single point. It's an infinite number of either numbers or points, okay? It's a portion of a graph. If you're looking at the graph, it's a whole region of a graph. Let's look at just a basic inequality to start with, just to remind you what an inequality looks like. What if you had an inequality looks like this, just 1 by itself? 1 minus 2x is less than 5. If that was an equation, none of you would have any problem doing that. And you shouldn't if it's an inequality. All you have to do is the same steps. Pretend like it's an equal sign in the middle, but just work with the inequality. And then right here on this last step, when you divide by a negative, you have to remember to flip the arrow. If you divide or multiply by a negative number, it's going to change the direction of the inequality relationship. And so instead of x is less than -2, we're going to get x is greater than -2. Now that means it could be a whole bunch of numbers. It could be any number greater than -2. And so we often show the solutions as a number line. And so you want to say it's anything greater than -2. So we put an open circle to show that it's not actually equal to -2. But we shade all the integers and all the real numbers that are greater than -2. We show a solid line showing that it's all those possibilities. Okay? Sometimes we have what's called a compound inequality. A compound inequality would look something like this. And that is where you have actually two inequalities built into one symbol. So you can look at it as this inequality and this inequality together. And you can solve it by solving it as two separate inequalities, or you can do it all at once. You can actually work with all three parts at the same time. So you can say, okay, I'm going to subtract 2 from both sides and the third side. And then you can divide by 3, again, on all three parts. And it works, except if you have to divide by a negative, then it does mess up the directions of your arrows. And so that's a little bit tricky. Did I do something wrong? This is 12. That's better. How about we go with 12? Because we're probably wondering if I'd lost my mind. It is late at night, I have to say. And so that's going to turn out to be 4. So then your number line ends up being the numbers x that are between -3 and 4. And notice there's a closed circle on the 4 end because it had an equal to bar underneath there, but an open circle on the -3. And then I'm going to shade the numbers that are in between because those numbers are both less than 4 and greater than -3, meeting both of those requirements. Okay, another type of inequality that we briefly looked at last year in Algebra 2 is an absolute value inequality. Absolute value is often used to represent distance in math. And so if we're saying the distance is greater than 3, we're actually saying two things. It could be that -2x plus 5 is actually greater than 3, or -2x plus 5 came out to be a -3, but the absolute value took away the negative. So we bring that negative back in, which flips the direction of the inequality arrow. And now we have two separate inequalities we have to solve. The steps are the same, but you get different answers on each side. This one gives us x is greater than, whoops, forgot to flip the arrow. X is less than 1. And then on this side, if we do the same steps, dividing by -2 on both sides, we get x is greater than 4. So that gives us a third possibility for the inequality. This time we get x is less than 1, or x is greater than 4. And even put the numbers in. There we go. So that's another possibility. This is an or situation right here, whereas this one up here was an and situation. So that's solving linear inequalities. All right, now if you have a system of inequalities, you may remember this from last year as well. Let me get some graph paper here so I can show you visually. Because if you've got two of them, for example, if you have y is less y, if we have y is less than 3x minus 2, and y is less than or equal to -2x plus 3, you may remember we got out colored pencils and we did all this. 3x minus 2, if we graphed that, it would go through -2 with a slope of 3. And then this is going to be a dotted line because we're not actually including the line, but we only want things that are less than the line. Remember, less than, this is the less than symbol right here. I know some of you have a hard time telling the difference. Less than, think of this as being like an L that's been squished down. Less than means below. And if you're talking to y, look at the y-axis, and where is it below the line? That would be all down here. So that means we're going to shade everything that is below that line there. And then the second equation, I'll do that in a different color. The second equation is -2x plus 3, so we're going to go up to 3, and we're going to go down 2 over 1, down 2 over 1, down 2 over 1. This one's going to be a solid line because it has the equal to bar there. And this one is also less than, and so less than for this one is going to go this way. Everything that's below the line on the y-axis. And so you can see our overlapping area. I know the colors get kind of messy here. Our overlapping area, it appears, is here, where the blue and the pink are crossing. Boy, those colors really don't go together, do they? That looks awful. But that's our shaded overlapping region there. Okay, so we did that last year in Algebra 2. So what if we throw into the mix some of the new functions that we studied in algebra last year, but also revisited at the beginning of the year, like an exponential function, and how about a logarithmic function? So this is the point where if you have a graphing calculator, you really have an advantage here because you can easily throw these into your calculator and see what they look like so that you don't have to just, start from scratch and really strain your brain trying to remember what these are going to look like. The first one is an exponential growth equation with a base e. E is 2.7, and then it has a +1 on it. So basically, you could plug some values in, E to the 0 is going to be 1. 1 plus 1 is 2. So I know that it's going to go through that point right there. I'm just thinking if I plug in 0, I'm going to get 2. And I know it's exponential growth. And it's got a solid line underneath it. So I know it's going to go something like this. Okay, that's my curve e to the x plus 1. Exponential growth, going upward, definitely going through 0, 2. I just use that as my base. Logarithmic curves, those have a vertical asymptote. And this one, it's going to have, let's see, it's going to be raised up. It's going to go through 5. Let me make a little graph for this one. Let's put in -1 so that we have the natural log. Oh wait, can't take the natural log of 0. How about we put in 0? We're going to get the natural log of 1, which is going to be 0, plus 5 is going to be 5. So we know it's going to go through 0, 5. That's right, isn't it? 5 plus the natural log of 0 plus 1. Yes, the natural log of 1 is going to be 0. 5 plus 0 is 5. Okay, double checking myself there. All right, and then the horizontal asymptote, yes, is going to be right at -1. So it's going to come up. Yeah, I can't take the natural log of 0. So I'm going to have an asymptote there. It's going to come up right next to that asymptote, and then it's going to go over here, and it's going to cross over somewhere there. Because it's going to have, now I made it dotted because this has a less than symbol, not a less than or equal to symbol. Okay, so I've graphed the two. I didn't even think about their inequalities except for whether to make it solid or dotted. But now I want to know where the region is that represents the solutions for both of these. So the first one is greater than the e to the x curve. And so greater than the e to the x curve would be everything that's above the e to the x curve. And then less than the logarithmic curve is going to be everything less than that. So hopefully you can see the overlapping area there is that kind of football shape, teardrop shape, I don't know what you want to call it, shape there in the middle. So those are kind of challenging because you have to remember how to graph two previous types of equations. Having a graphing calculator for this unit is going to be very, very helpful. Okay. We also did last year linear systems of equations where there was more than one, or more than two, sorry, that's what I meant, more than two. And we called that linear programming, and we did some examples of complicated word problems. But basically, I'm talking about something like this. X is less than or equal to 2, y is greater than or equal to -4, and then a third equation. This time I'll do a linear one, but it could be any other equation, quadratic or whatever. And so when you end up graphing this, you end up with maybe a 4-sided shape or a 3-sided shape, a triangle. I don't know, we'll have to see. So let's start with the first one. X less than or equal to 2. Well, x equals 2 is this solid line right here, vertical line. And to be less than that would be this way. Okay, it's nice to do it on this with all these nice colors. Y greater than or equal to -4. Well, y equals -4 is down here. And so greater than that is going to be everything above that. So far we're in this rectangular region where the yellow and the blue overlap. And then the third one, how do you want to graph that third one? You could put it into slope-intercept form, y equals mx plus b, or you could use the intercepts, plug in 0 for x to get the y-intercept, plug in 0 for y to get the x-intercept. I'm going to try that. If I plug in 0 for x, basically I cover up this. I have 6y equals 9, or y equals 9, 6, 3/2. And if I plug in 0 for y, that basically makes that 0. And then I get x equals -3. So I have 0, 3/2, 0, 3/2. And I have negative 3, 0, that's here. And those are the two intercepts. Now this one's a dotted line because it's just less than. It's not less than or equal to. So there's my line. And I want to be less than that. And so the less than means that I'm going to go this direction. Okay, it always gets messy when you do this, but you can see where the yellow, the blue, and the black overlap is this triangular region in the middle here. And so all the solutions are the points that are within that shaded, overlapping shaded region. Okay, now you're going to come across some word problems, and those word problems are going to ask you to come up with these equations yourself. So you're going to have to look at the words and turn them into inequalities like this to be able to answer these questions. But we did some of these last year. Again, they were called linear programming, for those of you that are still referring back to your Algebra 2 lesson. So look for those, and I will have another video posted later this week for the second lesson. All right, thanks guys. Bye-bye.